Welcome to week 5, Introduction to Machine Learning, where day 1 will be on machine learning basics and terminology. For day 2, we'll be looking at Introduction to Supervised Learning and Regression Models. For day 3, we'll be looking at advanced regression models, which are polynomial regression and regularization. For day 4, we'll be going over the introduction to classification and logistic regression. Day 5 will cover model evaluation and cross-validation. Day 6, we'll be looking at the k nearest neighbors or KNN algorithm. Finally, on day 7, we'll be doing our supervised learning mini project. So let's get started with week 5. Welcome to day 2, Introduction to Supervised Learning and Regression Models. Here, first we'll look at an overview of supervised learning and its application. The supervised learning is a fundamental machine learning paradigm in which a model learns to map inputs to outputs using labeled data. The process involves training a model on a data set that contains input-output pairs and then using this trained model to predict outputs for unseen data. Let's look at some of the key characteristics of supervised learning. First, labeled data. Supervised learning requires a data set with labeled examples, meaning each input has a corresponding known output. Examples can be inputs are features like the size of a house, number of bedrooms, or locations. Output is target variable like the house price. The objective or the goal is to minimize the error between the predicted output and the actual output, effectively improving the model's ability to generalize. The different types of supervised learning include regression, which predicts continuous outputs. Examples are predicting house prices or stock market trends. We have classification, which predicts discrete outputs, which are categories or classes. Examples are email spam detection or image classification. Let's look at some of the applications of supervised learning. In healthcare, we have predicting patient outcomes based on medical data. Example is diagnosing diseases like diabetes from patient records. In finance, we have fraud detection in transactions, credit risk assessment, these are the different ones. In retail, we can go with personalized product recommendation based on customer behavior. For autonomous vehicles, we have object detection and lane tracking using image classification. Now, supervised learning is widely used due to its straightforward approach and strong results in real-world scenarios where labeled data is abundant. Next, let's look at Introduction to Regression Analysis. Now, regression analysis is a statistical method for modeling the relationship between a dependent variable, a target, and one or more independent variables, which are the features. It is one of the most popular supervised learning techniques, especially for continuous output predictions. Let's talk about linear regression. Linear regression assumes a linear relationship between the dependent variable y and the independent variable x and aims to find the best fitting line through the data points. The equation of a line is y equal to beta 0 plus beta 1 x plus e, where BO or beta 0 is the intercept of the line where it crosses the y-axis, whereas beta 1 or b1 is the slope of the line, which is the rate of change of y with respect to x, and e is the error term representing the difference between the observed and predicted values. Now let's look at different steps in linear regression. First step is to fit the model, where we find the values of beta 0 and beta 1 that minimize the error between predicted and actual values. Next step is to predict, where we use the equation of the line to make predictions for new input values. Next, we evaluate. We assess the model performance using metrics like mean square error, MSE, and R-square. Now let's look at some applications of regression models. We have predicting sales, where analyzing the relationship between advertising spend and the sales revenue. In healthcare, we are predicting blood pressure based on age and weight. In real estate, we predict the house prices based on the features like the size of the house, the location, and the number of rooms. Next, let's understand the cost function and optimization in linear regression. Now, linear regression aims to minimize the error between the predicted and the actual values of the target variable. This is achieved using a cost function. Now, the cost function measures how far the predictions are from the actual values. For linear regression, the most common cost function is the mean square error, or MSE. This is a formula for it, where j of beta 0 and beta 1 equal to 1 raised to 1 upon m from I equal to 1 to m summation of yi minus beta 0 plus beta 1 xi the whole square, where m is the number of data points, yi is the actual value of the target for the ith data point, and beta 0 plus beta 1 xy is the predicted value of the ith data point. Now the objective here is to minimize the j of b0 or beta 0 beta 1 to find the best fitting line. Let's go over the optimization with gradient descent. Now the gradient descent algorithm iteratively updates the beta 0 and beta 1 to minimize the cost function, and that's our objective, right? So the update rule here is beta j is equal to beta j minus alpha of derivative of j to derivative of b of j, where alpha is the learning rate controlling the step size. Now the convergence here is the algorithm stops when the updates become very small or predefined number of iterations is reached. For visualizing the optimization process can be visualized as finding the lowest point on a cost surface. Next, with all this information, let's go ahead and look at our hands-on exercise. Our first step is to implement a simple linear regression model using scikit-learn. The objective here is to train a linear regression model and make some predictions. So let's get started with our exercise 1. Create a new file, Python file, save as inside my day2 underscore ex1.py. Let's start with importing numpy as np. Next, I need pandas. Import pandas as pd. Next, from sklearn dot model selection, I will import train testsplit. Next, from sklearn dot linear model, I will import the model linear regression, and then from sklearn dot metrics, I will import mean square error, which we have previously done it ourselves, but there is a library that is available, so we're going to use the shortcut this time, and R2 score. So that's available in scikit-learn metrics. Now let's go ahead and generate some synthetic data. So I will start with np dot random dot seed, so we get the same set of data. We'll start with that. Next, let's go ahead with x equal to np dot random dot rand and give it 100 comma 1 times 100 for x. Now for y, which we have done earlier, we do the same thing as the last week, 3 times x plus np dot random dot rand n 100 comma 1 times 2. So you've already gone through this before, so you are familiar with this. Now let's go ahead and split the data, which we did yesterday. So we're going to use something similar. We're going to get the x underscore train, x underscore test, y underscore train, and y underscore test equal to train test split, and to this I'll pass x, I'll pass y, which are the features and the target, test size equal to 0.2, and if you want to use the same seed, I'm going to say random state equal to 42. So every time it randomizes, it will get me the same data. Next, let's go ahead and fit linear regression. The way to do that is first we'll say model that we need is to initialize linear regression. Next, I'm going to say model. To this model, let's fit our features or the training data and the testing and the target set y underscore train. So I'm going to fit that here. Next, let's go ahead and make predictions. So to make predictions, I'm going to say y underscore pred equal to model dot predict based on our testing data set. So x underscore test. So now once we have this, let's go ahead and print the coefficients. So I'm going to say print coefficients, and first I'll print the slope, which is beta 1, sorry, which is comes from model dot coef underscore 0 at 0. So this will give me my slope, and the next thing that I need is intercept, which is beta 0, which will come from model dot intercept at index 0. Perfect. So this will give us our slope and intercept. So let's go ahead and run this. I'm going to say python day2.ex1, and there you go. We have our slope, which is 2.99, and intercept is 0.28 based on the random data that was generated here. So that concludes our training a linear regression model and making predictions. Our next exercise is to visualize the regression line and analyze the performance. So we'll use the same data that we've used before, but the objective here is to visualize the model's prediction and evaluate the performance. So I'm going to go back here inside the same exercise, and at the end of it, we have let's use import matplotlib dot pyplot as plt. So we have that. Given now we have our matplotlib, let's plot the data. I'm going to say plot dot scatter. We use the test data x underscore test, and for y I say y underscore test. Color that I'm going to use is, let's use blue, and label for this I will use as actual data. This is the actual data. Next, I'm going to create a plot with x underscore test, and I'm going to see what the predicted data is. Pred color equal to, in this case I'll say red because previous I said blue, label equal to predicted. So we can see the difference between the two of how close they lie. Next, I'll say title is linear regression model. For my x label, I'm just going to say x for now. For my, because we've randomly generated these numbers, y label, I'll say y. So my x and y, or maybe make it small y just to be consistent. Plt dot legend, I'll show the legend, and then I'll show the graph. I can also evaluate the performance. We have already imported MSE and R2 square. So let's go ahead and I'm going to say evaluate the performance of this, where I'm going to say MSE equal to mean square error, and this needs y underscore test. So testing data, compare it with predicted data. So this will give you the mean square error. R2 equal to, I'm going to say R2 score, and this needs the same thing, y underscore test and y underscore pred. So that's good. Now this I can print them out. I'm going to say MSE is MSE and print R squared is R2. Perfect. So I have everything here. So let's go ahead and run. We'll see the plot, and then when we close it, we'll see the MSC and R2. Now go here, clear this out, run this. I have my slope, intercept from before, and here is my actual or predicted line. And if you look at the actual data versus the predicted line, it's much in line. So it's much better data that we're getting. And if I go and look at the MSC is 2.61 and R squared, if it's close to 1, which means it's pretty good, and it's 0.999. So 3 nines is pretty good. And that's what we see from the graph, which is in line with the actual data. So we were able to implement a simple linear regression model using scikit-learn and visualize the regression line and analyze performance. So just to recap, today we understood the fundamental concepts of supervised learning and regression analysis. We also grasped the role of cost functions and optimization in training regression models. Then we went ahead and implemented and evaluated linear regression models using Python. Then we interpreted the model coefficients and performance metrics like MSC and R square. And finally, we also visualized the regression results to gain insights into models' effectiveness. So if you have any questions or have any problems implementing this, let me know and I'll get back to you. Day 3, Advanced Regression Models. Let's look at some advanced ones, which are polynomial regression and regularization. So first, let's jump into polynomial regression for modeling nonlinear relationships. Now, the polynomial regression is an extension of linear regression that models nonlinear relationship by introducing higher order terms of input features. Now, what is a polynomial regression? In typical linear regression, we have y equal to b of 0 or beta of 0 plus beta of 1x plus e. In polynomial regression, we extend this to include higher degree terms where we have y equal to b of 0 plus b1x plus b2x square plus b3x cube plus keep on going until bn x raised to n plus e. The inclusion of higher order terms allows the model to capture nonlinear patterns in the data. Now, the steps in polynomial regression include: first is feature transformation, where you create a polynomial feature from the original input data. Example, from x you create x, x square and x cube list. Next, you do model training, where you perform linear regression on the transformed features. Next, we do evaluation. We assess the model's ability to capture the data's nonlinear structure. What are the advantages of these? It's one is it captures non-linear relationship effectively. The limitations include prone to overfitting with high degree polynomials and may require regularization to avoid the overfitting. Example use case is predicting growth patterns in biological systems where relationships are nonlinear. Let's look at an example code for polynomial regression. So let's go ahead, create a new file. I'm going to say day 3 underscore samples. I didn't say 3, let's say dot py. Now we'll start with the libraries. We'll need import numpy as np. Next, we're going to say import matplotlib dot pyplot as plt for plotting graphs. Next, from sklearn dot preprocessing, I am going to import the polynomial features. Next, from sklearn dot linear model, we will import our model, which is linear regression. And then from sklearn dot metrics, for metrics we will import mean square error. These are libraries that we need. Now let's go ahead and generate some data. Synthetic data, always spell it wrong, synthetic data. and this data will be np. First we'll have to set the seed, random dot seed. So every time I run this code is the same data that we get. X equal to np dot random dot rand. So don't get me wrong, you'd get the same data, but it's randomized data, times 10. Next we'll get y equal to 3. So we probably did this last week. 3 times x, we need square, plus 2 times x plus np dot random dot randn 100 comma 1, and we'll say times 5. So we have x and y data. Next, go ahead and transform features to polynomial. Now to do this, I'm going to say poly features. I'm going to create a variable poly features and call the polynomial features. The degree that I'll use is, I'll use a smaller degree of 2, and I'll say include bias equal to false. Don't include biases in this. I'm going to say x underscore poly equal to poly underscore features that we have above. Let's say fit transform and pass x to this. So this is how we can transform features to polynomial. Next, we'll fit the polynomial regression. So to do that, I'm going to say fit polynomial regression. And as I mentioned, you just fit the linear regression to it by saying linear regression first, initialize this. Next, model dot fit, pass the x underscore poly and y, and then y underscore pred equal to model dot predict x underscore poly. So this is how you fit the polynomial regression. Now let's go ahead and plot the results. So I'm going to say found plot the results. I'm going to move it up a little bit so it's clear. Here, first I'm going to use the scatter, plt dot scatter, pass x, y. I'm going to use the color of blue for the scatter plot, and label, I will say this is the actual data that we have. So that's what we are displaying. Next, I'm going to say plot dot scatter. In this particular case, I'm going to say x comma y underscore predicted data here. So color equal to red I will set here, and then label equal to, in this case it's predicted data. Next, I'm going to set a title which is polynomial regression. Once I'm done with that, I'll put my x label, and that I will use x, the data that we've used, dot y label. For this, I'll use y. And next, I'll say legend. So we labels get displayed properly that we have created above here. And then I'll say plot dot show. So this will show us our scatter graph of actual data and predicted data. Now, finally, let's go ahead and evaluate the model since we have the mean square error. We're going to say MSE equal to mean square error, and this needs our y and y predicted data to compare. Now say print mean square error or MSE is equal to comma MSE. So let's print this out. So let's go ahead, and that kind of shows how to implement polynomial regression. I'm going to go ahead and open my terminal here, and I'll say Python day 3 samples. First, it will show my plot data. So if you see the actual versus plot, actual is in blue and red is our predicted data, is much similar to what the actual data is. So it looks pretty good. The model worked pretty well. Next, let's look at the mean square error. Our mean square error is 19.42, which looks pretty good. So that's how you implement polynomial regression. Next is introduction to regularization techniques. We'll look at lasso and ridge regression in this particular case. So what is regularization? Regularization is a technique used to prevent overfitting by adding a penalty term to the cost function of a regression model. This discourages complex models by reducing the magnitude of the coefficients. The different types of regularization that we have is first is the ridge regression, which is also called as L2 regularization, which adds the sum of squared coefficient to the cost function. This is how it looks like. J of beta equal to 1 divided by n, summation of I equal to 1 to n, y of I minus y cap of I squared plus lambda of j to I to p summation beta j square. The lambda here is the parameter that controls the strength of the penalty. Next, we have the lasso regression, which is also called as L1 regularization, which adds the sum of the absolute coefficients to the cost function. If you look at the formula, it looks almost same as the previous one, but at the end it's a little bit different, where I'm saying j of beta equal to 1 divided by n, summation of I to 1 to n, y of I minus y cap of I squared plus lambda of j of I to p. Here is where we do kind of an absolute summation of b of j or beta of j. So this encourages the sparsity in the coefficient, effectively performing the feature selection. The key differences is the ridge shrinks coefficients but does not eliminate them, whereas lasso can shrink some coefficients to zero, removing irrelevant features. Next, let's talk about avoiding overfitting with regularization. Now, regularization reduces the risk of overfitting by controlling the complexity of the model. The regularization parameter lambda, also called alpha in some libraries, plays a critical role. Now, the role is a high lambda value increases the penalty, forcing smaller coefficients and reducing overfitting, whereas a low lambda value allows the model to fit the training data more closely, increasing the risk of overfitting. Now let's look at an example code for this lasso and ridge regression. So I'm going to go ahead, clear this out. Let's create a new one. I'm going to call day3 underscore samples 2.py. Here, first we need ridge and lasso, and that is available from sklearn module. Inside linear model, I'm going to import the functions for ridge and lasso. Next, I need the train test split, so I'm going to say from sklearn dot model selection, I will import the train test split. Now, for the data that we have, I can directly use the data from before where we have created this. Let's take the entire poly data so to we see how we can use this to avoid overfitting. So I'm going to just put that here. Now it needs numpy. I'll copy this, paste it here. Next we need polynomial features. I'm going to take that, and actually let me take the entire thing. It doesn't harm to get the libraries. Okay, so that kind of gives me the xpoly. So now let's split the data into training and testing sets. So I'm gonna use that train test split here. I will use x underscore poly. I'm gonna use the y set. We are gonna say the test size equal to 0.2, which is again 20% is for testing and 80% for training. And I'll set a random state of 42. So this will give us x underscore train comma x underscore test, y underscore train, and y underscore test. So that's what we will get here. Perfect. Next step is to use the ridge regression. So I'm going to say ridge regression. For this, I'm going to say reg underscore model here equal to reg, and to that I'll give a alpha of 1, and then I'm going to say reg model dot fit and pass it x underscore train and y underscore train to fit the data and train the model. So then I'll say reg underscore, let's do predictions, equal to reg model dot predict and pass it x underscore test. So this is our ridge regression done here. Next, let's do the lasso regression. Lasso regression. This is lasso underscore model equal to lasso. Similarly, we'll say alpha float equal to 1, alpha equal to 1, lasso model dot fit, pass it the x underscore train, y underscore train. Next, I'll say lasso underscore predictions equal to lasso model dot predict, pass it x underscore test. Now let's go ahead and evaluate. Now we're done with ridge and lasso. Let's go and evaluate first ridge. So I'm going to say ridge underscore MSE, mean square error, or MSE equal to mean square error y underscore test, and let's give it the ridge predictions that we have. Let's go ahead and print the ridge regression MSE here, which is ridge MSE. Perfect. So we have done that. Next, let's go ahead and evaluate lasso. So it's almost the same code as above, but instead of ridge, I'm going to say lasso MSE, mean square. Instead of ridge, I'll say lasso predictions, and then here I'll say lasso MSE, and I'm going to say lasso regression MSE. Perfect. So that's all. So let's go ahead and print this out. Let's try it out how it looks like. So I'm going to go ahead, open my terminal, run my day 3 samples 2, and we have a ridge regression MSE of 15.8 and lasso regression MSE of 16.2. A little different, but you see why we went through those to understand the values of why it does help with the overfitting part. So next, let's go for our hands-on exercise. Here, first we'll be implementing the polynomial regression and visualize the fit. The objective here is to use polynomial regression to model the relationship between the median income and the median house value. The steps that we will follow here is first we'll load the California housing data set. We'll select the feature medium income and the target variable medium house value, which are available in the dataset, and transform the feature into polynomial features. We'll fit a polynomial regression model and visualize the fitted curve and analyze the performance. So let's go ahead and start coding this. I'm going to clear this out here. Close this, close this. I'm going to create a new file, and this one I'm going to say day 3 exercise 1.py. Now let's start with the libraries. I'm going to say import numpy as np. Next, I'm going to say import pandas as pd. Next, I need matplotlib, so import matplotlib.pyplot as plt. Next, I am going to get sklearn dot data sets. Now this will contain my data set, which is the California housing data. So I'm going to say import fetch California housing data. Next, from sklearn dot pre-processing, I am going to import the polynomial features which we did before. Next, we are going to get the from linear model, we will import linear regression. Next, from sklearn dot metrics, I am going to import mean square error to check mean squared error to test the or evaluate this particular model. So now first thing is load the California housing data set. Now this is the first time we are loading a data set from a sklearn data set. So to do that, what you do is you just say data equal to fetch California housing, and as a frame, as data frame equal to true. Oops, let's see what we have written as frame equal to true. So this gives me a data frame. So I can just say df equal to data that we have above. Oops, I think I instead of equal as dot frame. So this will give me my data frame from this data that we fetch from the California housing data. Next step is to select feature, which is in this particular case median income, and target, which is the median house value. Now these are some of the columns that exist in the data set. You can actually say df, you can use the df dot head to look at first few 5 rows to see how it looks like. But since I already know it, I am going to just go ahead and implement this. I'm going to say the feature is median income and y is the df of we need the median or med house value, median house value. So these are our features and targets. So once we have that, next thing I need is to transform feature to polynomial features. Again, we'll use the degree of 2 as we did in our examples. So I'm going to say poly. You can increase the degree if you want, but I'm just going to stick with 2. Degree equal to 2, and I'll say include biases equal to false. You can include this if you want to include bias. Score poly equal to poly dot fit underscore transform and pass it the value x. Next, let's go ahead and fit polynomial the polynomial regression model. To do that, first I need to get the model, which is linear regression. Next, I'm going to say model dot fit and pass it x underscore poly and y. Now once I'm done with this, let's go ahead and make some predictions. So to make predictions from the data set that we have, I can say y underscore pred equal to model dot predict, and this I'll pass x underscore poly, and let's go ahead and plot actual versus predicted values. So first I'll say plot dot figure for my diagram. I'll say figure size equal to 10,6 width and height. That's what we specify here. Next I'm going to say scatter plt dot scatter x comma y. We give a color of blue. Next we say label equal to, remove this, actual data, and alpha equal to 0.5. Next another scatter. This time we'll give x comma y underscore pred color equal to red, label equal to predicted curve, alpha equal to 0.5. Next, let's give a title. In this particular case, let's say polynomial regression median. No, I'm not going to give more than that. I'll just say polynomial regression. I was going to say for California housing data, but I'm going to stick to that. I'm going to use here, say median income in California, plot dot y label is median house value in California. Now plt dot legend, show the legend, and I want to see the plot, show. So that's about it. Next thing that we want to do finally, let's go ahead and evaluate this model. Evaluate model performance. To do that, MSE equal to mean square error. We pass y and the predicted value y pred. Next, let's go ahead and print the mean squared error, also called as the MSE, comma MSE. So there you go. Our entire code is done for a real data set, in this case the California housing data. So let's go ahead and run this and check it out how it looks like. So I'm going to open this, Python day 3 ex1 py, and there you go. Since we have a lot of data here, because it's all the California houses, or I guess a big huge chunk of that data, and that's what you'll see. This is the our actual value that is displayed here. There are some outliers, and we have the predicted curve which sits right in the actual data set. If you see, the data set is somehow curved in this direction, and our predicted curve is also in the same direction. So given a median income in California, you can actually tell what is their house value in California. So I hope you were able to follow along. Let's go ahead and do our next, which is use lasso and ridge regression. Now here we will train lasso and ridge regression model on the same California housing data set and observe the effect of regularization. We'll use the same features, medium income and target variables, and apply polynomial feature transformation degree 2 and split the data into training and testing sets and train lasso and ridge regression models with different regularization parameters, and finally evaluate the models using the MSE or mean square error. So I'm going to go ahead and use the same exercise, and here at the end I will say from sk learn dot linear model I need to import ridge and lasso, and next from sklearn dot model selection I will import, I think I already have the, no I don't have the train test, import train test split. These are two things that I need. Now I will go ahead, and after my poly is found here, I'm going to comment this out because I don't need any of these, but the path is pretty much same. But here I'm going to say split data into training and testing sets. So first I'm going to say x underscore train, x underscore test, y underscore train, y underscore test equal to train test split. Pass it x underscore poly. I'll say y. I will give test size equal to 0.2, and I will say random state equal to 42. Next, let's go ahead and do the ridge regression. Here I'm going to say ridge RIDGE model equal to ridge and give an alpha of 1. Next I'm going to say ridge model dot fit and pass it x underscore train and y underscore train, and then I'll say ridge underscore predictions equal to ridge underscore model dot predict and pass it x underscore test here. So we have a ridge regression. Next, as you know from our example that we did, is lasso regression. I'm going to say lasso underscore model equal to lasso, give it an alpha of, I'm going to give a 0.1 this time, adjust alpha for like sparsity in this particular case, and I'll say lasso underscore model dot fit x underscore train and y underscore train. Next, I'll say lasso underscore predictions equal to lasso model dot predict and give it the value of x underscore test. So we have ridge regression done and lasso regression done. Next thing, we will go ahead and evaluate the ridge regression. That can be done using ridge underscore MSE equal to mean squared error and pass it y underscore test comma ridge predictions. This will give us our ridge MSE. So I'm going to say ridge regression. Day 4, Introduction to Classification and Logistic Regression. Today, let's start with understanding the classification problems and common use cases. Now, what is classification? Classification is a supervised learning task where the objective is to predict a discrete label, in this particular case, a class, for given input data. Unlike regression, which predicts continuous outcomes, classification assigns categories to data points. Some of the types of classifications include, we have binary classification, where there are two possible outcomes. It's either a yes or no, or in email cases, it can be spam email or not a spam email. Example can be predicting whether a customer will make a purchase. That is, either they will make a purchase or not. Then we have multi-class classification, where we have more than two classes. Example, you can say the image belongs to a cat, maybe a dog, maybe a rabbit, or maybe a squirrel. So this is a good example case of image classification where multi-class classification is used. Then we have multi-label classification, where you can predict multiple labels for a single instance. Example, predicting tags for a blog post. So you have multiple labels for the same item. Next, let's talk about some common use cases. It's used in healthcare for diagnosing diseases. Example, cancer detection based on medical images. You can use it in finance for fraud detection in transactions. If you're in the retail field, it can be used for predicting customer churn or purchase behavior. In natural language processing, it can be used for sentiment analysis and also, as I mentioned, spam detection. Also, for autonomous systems, you can do object detection for self-driving cars and kind of detect and tell whether it's an object or not an object. Classification is the cornerstone of machine learning and underpins many real-world applications, including the ones that we just spoke about. Let's talk about logistic regression for binary classification. Now, first, what is logistic regression? Logistic regression is a statistical method used for binary classification. It predicts the probability that a given input belongs to a specific class. Let's talk about the logistic regression model. The equation for this says that a logistic regression applies the sigmoid function to a linear equation and is represented by p of y equal to 1 to x equal to sigma of beta 0 plus beta 1 x1 plus beta 2 x2 plus all the way to beta n xn, where p of y equal to 1 to x is the probability of the positive class and the sigma of z is the sigmoid function. Let's dig deep into the sigmoid function here. Now, the sigmoid function maps the output to a range between 0 and 1. The sigma of z is equal to 1 divided by 1 plus e raised to minus z. Now, if P of y equal to 1 to x is greater than 0.5, the prediction is class 1. Otherwise, it is class 0. That's how this formula works. Now, next, let's talk about the decision boundary. The threshold default is 0.5 used to classify instances, and decision boundaries can be adjusted to optimize for precision or recall. Let's talk about the interpretation of these coefficients. We have, as you saw in the previous slide, we have beta 0 and beta I. Beta 0 is the intercept, the baseline probability, and beta I is the effect of a feature xi on the log odds of the positive class. So I is represented by the number at which the feature is used. Next, let's talk about more on sigmoid function, decision boundary, and interpretation. Now, the sigmoid function ensures outputs are interpretable as probabilities. The visualization of the sigmoid function can illustrate how probabilities are mapped from raw model predictions. Next, decision boundary. Now, default threshold, as I mentioned, is 0.5. Adjusting the threshold can balance precision and recall depending on the use case. Example, prioritize recall for fraud detection. So let's go ahead and see how we can implement sigmoid function and generate some values and plot them on a graph. So I'm going to go open my Visual Studio, say Python file, and here save it in my day 4 underscore sigmoid. That's what I'll call it. First, let's import numpy as np. Next, I need to plot, I need matplotlib.pyplot as plt. So next, let's implement the sigmoid function here. I'll create a function, and this will take the z value. Oops. And inside here, I will return, as I mentioned, 1 divided by 1 plus np.exp of minus z. That's the sigmoid function. Next, let's generate some values. To do that, I'm going to say z equal to np dot linspace. I want the values between minus 10 to 10 and in hundreds. Next, I'll say sigmoid underscore values equal to sigmoid of pass the value z to it. So call that function above. Now let's go ahead and plot it. So I'm going to say plt dot plot z and sigmoid values. Not gonna do anything else, just keep it default. Plot dot title sigmoid function. Next, let's give it a x label where I am going to use for x coordinates, as you've seen above, I've used the values of z. So I'm going to say z, and I'll say plot on the y. I am using sigma of z. I can also use the sigma notation here and just do something like this, sigma of z. Those are some of the symbols that are available if you want to use. Plot dot grid and plot dot show. So as a grid it will show. So let's run this and see what do we get. I'm going to say Python day 4 sigmoid, and there you go. We have our sigmoid functions based on the values from minus 10 to plus 10 in the hundreds, and then it goes from 0 to 1 depending on what the values are. So there you go. So that's the implementation of the sigmoid function. Next, let's go ahead and do some hands-on exercise. First, we will be implementing a logistic regression model to classify a data set. Example can be predicting if a customer will make a purchase. So if you want to try it, go for it, or pause it here and then implement it, and then we can come back and look at the solution. So first, let's go ahead. The objective here is to train a logistic regression model to classify customers as likely to purchase, which is 1, or not, which can be 0, based on their behavior. Now the dataset we'll use the social network ads dataset available in many online resources, or generate synthetic data. So we'll pick one of them. So in our case, we'll just generate some synthetic data, but the best practice is use one of the dataset that is available. So the steps what we'll be doing here is, first we'll load and pre-process the dataset. For the dataset, you can use something that is available globally or through some of the websites, or what we will be doing here is we can generate some synthetic data for it. The steps that we will follow is, we'll kind of divide it into 4 steps. First, we'll load and pre-process the dataset. Next, we'll split the data into training and testing sets. Next step, we'll train a logistic regression model. And finally, we'll evaluate the model using classification metrics. So let's get started. I'm going to say wait as day 4 underscore exercise 1 dot py. Now here, first I am going to import my libraries, pandas as pd. Next I will import numpy as np. Next I will, from sklearn dot model selection, I will import train test split to split the data. From sklearn linear model, I will import logistic regression, and from sklearn dot metrics, I will import the different tools, which are accuracy score, precision score, recall score, and F1 score. So these are the metrics that we'll be using. We can also use the classification report, since we're gonna do a classification task. So these are the ones that you need. I hope you got that. Next, let's go ahead and generate synthetic data set. For this, I'm going to say np dot, so first set the random seed. So every time we run this code, we get the same data set. N underscore samples equal to 200, x equal to np dot random. So to create our features, I'm going to say rand n underscore samples comma 2 times 10. This is the features which are, we think of it as like age and salary. And then y equal to, I'll say x of from colon to 0 times 1.5 plus, I'll say x of colon to 1 greater than 15 dot as type, and convert that to int. So this will be a target, which is purchases, which will be either 1 or 0 depending on the value. So these are all generated randomly. So now next, go ahead and let's create a data frame and say df equal to pd dot data frame, pass it x, and the columns that I want to create for them, I'll call them age and salary, because above I did not actually mention that. So that's what it will create a data frame. Now for purchases, I will use whether it purchase was made or not equal to y. So this is how you can create a synthetic data set and assign it to a data frame. Next is to split this data into training and testing. So we get the x train, x test, y train, and y test. That we can get from our train test and then pass it our data frame here. Now we have to pass for the x. I want to just give the ones that are features, which is df of age and salary, the one that we have created above. Next, For Y, I want to use the purchases. So I'm going to say df data frame of purchase. Next, so I think I have an extra here. Okay, this one closes this one. Okay, purchase. And test size, I will specify 0.2, which means 20% is used for testing and 80% is used for training. Random state equal to, I'll give a seed of 42, which makes sure that every time this runs, we have the same testing and training data set split. So I am going to say next, train the logistic regression model. So this is my next step where we will be training the logistic. We have done this previously where we first initialize the logistic regression model, calling it. Next, I'm going to say model dot fit and pass it x underscore train and y underscore train. Now let's go ahead and make predictions. Y underscore pred equal to model dot predict x underscore test. Now let's go ahead and evaluate performance. So first, based on all the metrics that we have downloaded, we are going to first start with accuracy, which is accuracy score, and what it needs is it needs the testing data set plus the predicted data set, which are the targets. Y underscore test. So this will compare y test with y underscore pred and tell me how well the model predicted, how accurate the model is. 1, 2, we precision, recall, F1 and classification report. So I'm going to say precision. What is the precision? We'll do one for recall, we'll do one for F1 score, and we'll do one for, let's move it in the next line here and say classification report slash n. This is a little bit fancy one, that's why we do a little bit more. Now here all we have to do is change it to precision score. The parameters are same, recall score, F1 score, and finally we give the classification report. So this will give me my performance based on the model that we've created and trained based on the data, synthetic data that we have here. So I am going to save this and go back here, make sure my previous one is closed. So clear it out. Python day4 underscore ex1.py, run it. It will go through it and it is giving an error here. Looks like instead of 1.5 I said 1,5. Clean this up, save it, go back, clear it out and run it again. And there you go. We have accuracy of 1, precision of 1, recall of 1, F1 score 1. Which makes sense because we are using synthetic data and everything is perfect. Usually when you use some real data sets, it might give you a different values, but the classification report, as you can see, from 0 to 1, precision is 1, everything is pretty much perfect. Accuracy, macro, average, weighted average, everything is 1 because the data is perfect and the model is going to predict perfectly for whatever data you give based on the values that we have generated here. So there you go. So you kind of learned how to train a logistic regression model to classify customers as likely to purchase or not based on their behavior data, which is age and salary. This is what we mentioned. So given anyone's age and salary, if you input that data here and want to see if that person want to purchase your item, you can kind of predict properly. Next, so our second exercise is analyze model performance. Now we already got evaluated the performance. Now here we'll be visualizing the decision boundary and analyzing the model predictions. So we are going to use the same exercise, same data, and we'll just add this additional plot to it. So I'm going to go at the bottom here and I'm going to import matplotlib as pyplot as plt. Next, I am going to plot the decision boundary. Now to do that, I want to get x underscore min, comma, x underscore max values. That is coming from x of age dot minimum minus 1 comma x of age dot max plus 1. So that will give me the minimum x and maximum x. Next, for the same thing for y underscore min comma y underscore max, I am going to use x of salary dot min minus 1 x of salary dot max plus 1. Now let's get xx and yy. This is np dot me mesh grid is what I am going to use here, and get my values from np dot range x underscore min and x underscore max 0.1. So this will create my mesh grid with other value of np dot range and pass y values here, y underscore min comma y underscore max comma 0.1. So that will give me my mesh grid based on the values. Now let's go ahead and predict the probabilities for grid points. So I'll say predict probabilities for grid points. To do that, I'm going to use z equal to model dot predict, call the predict function, pass it np dot c underscore, and I'll give xx dot ravel them ravel and then yy dot ravel. So that gives me predictions. Next, I'll say z equal to z dot whatever values we get, let's reshape them based on xx dot shape so it fits perfectly. And then finally, let's go ahead and plot them. So I'll say plot dot, so I'm going to use the contour plotting method, contour f, and I'll pass xx dot yy z alpha equal to, let's make it 0.8, and c map equal to cool warm. So I have my contour. Then let's go ahead and do the scatter graph. I'm gonna pass x underscore test, where we'll pass the age first, age. Then I'll pass x underscore test, pass the salary. Then I will specify c equal to y underscore test for this, and then edge color for this scatter will use k, and c map will be, again you'll use the cool warm. Perfect. So that kind of takes care of our scatter plot. Next, give it the title. For the title, I'm going to say logistic regression decision boundary. So this will give the title on the top. Then X label is the data that we have passed. In this case, we have passed age as the data. For my Y label, I'm using salary. X is this, Y is salary. Next, I am going to say, just let's show it. So that's it. So let's go ahead. I'm going to clear this out, run this. So it ran with the previous data that we have printed above, but it also gave me an error saying that age and the reason is we have created those columns as in the data frame, not in the actual data set. So we'll use something similar to what we did here. For age, it's the first column, so I'm going to use that, and for the salary is the second column, so I'm going to use that here. Oh, looks like there's an error here, xx of yy dot ravel, so that should be good, or else we've gotten another error. Clear this out, let's run it again, and there you go. We have our scatter plot data, our decision boundaries right here. There's a couple of items which are on the decision on the boundary, but as you can see, it properly allocated them either on the positive space or 0 or 1 depending on the data that we have. And it's a pretty good data set, widely spread across from age wise and based on salary, and was properly able to tell us if the user is able to purchase or not make a purchase. So I hope you were able to follow along. I'm going to close this out and implement this code. If not, let me know if you had any issues or any problems, and I can get back to you. So today, just to summarize, we kind of went through understanding the classification problems and their real world application. We got into the fundamentals of logistic regression, including the sigmoid function and the decision boundaries. We were able to implement a logistic regression model to classify the data, and we evaluated model performance using metrics like accuracy, precision, recall, and F1 score. And finally, we were able to visualize the decision boundaries and interpret model predictions in text as well as in on a graph. So I hope you were able to follow along. If you have any problems or questions or doubts, let me know and I'll get back to you. Day 5, Model Evaluation and Cross Validation. Today, we're going to look at model evaluation metrics for both regression and classification. Let's start with model evaluation for regression. Now, regression models predict continuous values and their performance is measured using error metrics. First one is mean squared error, or MSE, which measures the average square difference between predicted and actual values. It's sensitive to outliers due to the squaring of errors. Next, we have mean absolute error, or MAE. This measures the average absolute difference between predicted and actual values. It provides a more interpretable measure but less sensitive to outliers. Next, we have the root mean square error, or RMSE. Now, this is the square root of MSE, which is the mean square error above, providing errors in the same units as the target variable. Next, let's look at model evaluation for classification. So classification models predict discrete classes, and their performance is evaluated using metrics derived from confusion matrices. So we use accuracy, which is proportion of correctly predicted instances. Now, if you want to look at how accuracy is predicted, it's always true positives plus true negatives divided by true positives, true negatives, false positives, and false negative. It's useful when the data set is much more balanced. Next, we have precision. Precision is the fraction of positive predictions that are correct, which is, so that's why it's kind of formula goes like true positives divided by true positives plus false positives. So only positives are used here. It's important for applications like fraud detection where false positives are costly. Next, we have recall, which is also called as sensitivity, which is fraction of actual positives that are correctly identified. So it's true positives divided by true positives and false negatives. It's useful in cases where missing positive instances is critical. Example can be a medical diagnosis. Next, we have F1 score. This is the harmonic mean of precision and recall. So F1 is always plotted as 2 times precision type times recall divided by precision plus recall. It balances precision and recall, especially useful for imbalanced data sets. Next, let's go over cross-validation. Cross-validation is a robust model evaluation technique that provides a more reliable estimate of model performance by splitting the data set into multiple training and testing subsets. So some of the key cross-validation techniques include we have the k-fold cross-validation, which splits the data set into k equal parts or folds. It trains the model on k minus 1 folds and tests on the remaining fold, repeating the process k times. The average of the k test scores provides the final evaluation metric. Next, we have the stratified k-fold, which ensures each fold has a proportional representation of classes in classification problems. We also have leave one out cross validation, or LOOCV, which trains the model on n-1 samples and tests on the remaining one, repeated for all samples. computationally very expensive for large data sets, as you can imagine, because you're kind of doing n minus 1 training and testing on one every single time. Advantages of these are it reduces the risk of overfitting by testing on multiple subsets of data. It also provides more generalized evaluation of model performance. Next, let's understand the confusion matrix. The confusion matrix is a table that summarizes the performance of a classification model by comparing predicted and actual values. Here is the structure of confusion matrix where we have actual positives and actual negatives, and on the column side we have predicted positive and predictive negative. This kind of gives us the combination of actual positive and predictive positive gives us the true positive, actual negative and predictive positive gives us the false positive, actual positive and predictive negative gives us the false negative, and actual negative and predicted negative gives us the true negatives. Now, the key metrics derived here are, as you can see above, is true positive rate, TPR, which is same as recall. We also have false positive rate, which is FPR, which is the proportion of negatives incorrectly classified as positives. And we also get the specificity, where proportion of negatives are correctly classified. Now next, let's go on do a hands-on exercise for today. Today, we'll be looking at evaluating a model using cross-validation to obtain a more accurate estimate of the model performance. So objective here is to use the k-fold cross-validation technique to evaluate a classification's model performance. So let's go ahead and implement this. Create a new file. First, let's get our libraries from sklearn dot datasets. I will import load iris. That's the data set I want. So I'm going to save it as day 5 underscore exercise 1. Next, I am going to say from sklearn dot model selection. I will import cross val predict, cross val score and k-fold. Next, from sklearn dot ensemble, we need the random forest classifier here, so I'm going to import random forest classifier. So while these are used, let's go ahead and first load the data sets to see why each and every library is used. So first, for data, I'm going to load iris, the iris data set. We're going to get it directly from our data sets in sklearn. And x comma y here, I am going to say whatever data I get, take the data from there, and from there, whatever the target is, I'll take the target and assign it to x and y. Next, we will initialize the classifier. Now, you probably might be asking, why didn't I use this iris dataset before? Because I just want to show you, if you want to import something from outside, how that works. And this is more of a shortcut if you want to play around with the existing datasets that we get. Model equal to random forest classifier, and I'll give a seed of 42. Now next is perform k-fold cross validation. So for this, I am going to say kf equal to k-fold, and I will say here n underscore splits equal to 5. It needs 3 parameters. The number of splits that I want to do, the shuffle I want to do is true, if I want to shuffle or not, random state equal to 42. So the same data set is used every single time. cv underscore scores. So let's look at the scores. For that cross validation scores, I'm going to use this cross val score, pass it model, pass it x, y, it needs cv equal to which one, k-fold, and scoring equal to accuracy. That's what I'm going to use. So that will give me my cross validation score. Now let's output these results. First, I want to print the cross validation scores by saying CV underscore scores. Next, let's print the mean accuracy, that is CV underscore scores dot mean. Perfect. So I have these. So let's go ahead, save them, and then let's run them here. I am going to say Python day 5 exercise 1, run it. Going to take some time because of the number of times it goes through the entire thing. And here is my cross validation score: 1, 0.96, 0.93, pretty good. And my mean accuracy is 0.96, very close to 1, which is pretty good. So we were able to use k-fold cross validation to evaluate a classification, which is a random forest classifier's performance. Our next exercise is to generate and interpret a confusion matrix for a classification model. So what we are going to do is we are going to train a logistic regression model and generate a confusion matrix for evaluation here. So let's go ahead, and I'm going to create a new file, call it day5 underscore ex2.py. Now here first let's go, and from sklearn I need the linear regression, so that is inside linear model. I am going to import logistic regression. Next, from sklearn dot metrics, I need to import confusion matrix. I need confusion matrix display, and I also need the classification report. So perfect. Next, I will from sklearn dot model selection import our favorite one, train test split. So now first let's load the data set. Now this data set is what we used in the previous one, x and y. So I'm going to use copy this, paste it here. I doesn't know what load iris is because this is here. So I need to import that too. Okay. So now next step is to load the data set. Load data set into xtrain training and testing models. Xtrain, x test, y train, and y test equal to train test split, get my x, get my y, test size equal to 0.2, and random state equal to 42. So now that my data set is available, I am going to train the logistic regression. Let's say train logistic regression. To do that, I'm going to say model equal to logistic regression. We can add how much iterations we want. I can say max iterations equal to 200 just in case. Model dot fit, I will fit x underscore train and y underscore train. So I have my model trained now. Next, I will predict on test data. To do that, I'll say y underscore pred equal to model dot predict, and to this give x underscore test. I'm gonna predict on that data. Next, let's generate the confusion matrix. Now to generate the confusion matrix, I'm going to create a variable cm equal to confusion matrix and pass it y underscore test and the predicted values y underscore pred. Now finally, let's display confusion matrix using the confusion matrix display function. So I'm going to say confusion matrix display, pass it the confusion matrix, which is our CM. Next, it needs a display labels, which is what are the labels that we are using. We are going to use the data based on the target names, which is probably our iris data. Next, let's say display dot plot and show the C map in what color do you want. Let's use blues. Next, I will say plot dot show. Let's make sure we don't have the plot available, which means I'll have to take it from, I'll have to import that from matplotlib.pyplot as plt. So plot should be good. Next, import matplotlib.pyplot as plt. So that should be good. Perfect. Next, I am going to say print our classification report. To do that, all I'll do is print, make it a new line, classification report /n. Since it's a proper report, I'm going to say classification report, give it y_test and y_pred. Perfect. So that's our completion of our exercise 2. The expected output here should be a nice classification record based on precision, recall, F1 score, and accuracy. And let's also see if we can check out the confusion matrix display. So I'm going to go here, clear it out, and I'll say Python day5 ex2.py. Looks like I have mentioned target name instead of target names. Let's go back, clear it out, run it again. And there you go. We have our confusion matrix displayed here nicely based on Cetiso, versicolor, Virginia. These are the different Virginica. These are different species. So that's what we have here, perfectly mapped. And if I close this, I have my precision, recall, F1 score, and support displayed here in a classification report perfectly. So I hope you were able to follow along and get this implemented. So just to summarize, today we understood and implemented evaluation metrics for regression and classification models. We performed the k-fold cross-validation to obtain robust model performance estimates. We generated and interpreted confusion matrices for classification models. And finally, we gained some practical insights into balancing precision and recall for specific use cases. I hope you were able to follow along. If you have any questions or had any issues, let me know and I'll get back to you. Day 6, K nearest neighbors KNN algorithm. Let me take you over this by starting with the introduction to the K nearest neighbors or KNN algorithm and its applications. Now, what is K nearest neighbors or KNN? K nearest neighbors is a non-parametric instance-based machine learning algorithm used for both classification and regression tasks. It relies on the similarity between data points to make predictions. Some of the key characteristics include instance-based learning. The model does not explicitly learn a mathematical function during training. Instead, predictions are made by comparing test data to stored training data. We also have distance metrics. KNN uses distance measures, example Euclidean, Manhattan, Minkowski, to find the k closest data points, or also called as the neighbors. Classification. It predicts the majority class among the k nearest neighbors. And finally, regression predicts the average of the target values of the k nearest neighbors. Some of the applications of this include image recognition, where classifying images based on pixel similarity, recommendation system for finding similar users or input or items, medical diagnostics, predicting diseases based on similar patient profiles. Also, we talk about customer segmentation, grouping customers based on purchasing behavior. Now let's look at how KNN works for classification and regression. Let's go through this in step-by-step process. First step is feature scaling. Now, since KNN relies on distance, feature scaling, example min-max scaling or standardization, is essential to ensure all features contribute equally. Second step is to calculate distances. Compute the distances between the query point and all training points using a chosen metric. Example, you can use the Euclidean distance. Next, identify the k nearest neighbors. Sort all points by distance and select the k closest points. Finally, make predictions. Now, for classification, assign the class most common among the k neighbors, which is also called as the majority vote. And for regression, predict the mean or weighted average of the target values of the k neighbors. Now let's talk about choosing the optimal value of k. So for choosing k, we can use small k by using high sensitivity to noise or overfitting, or capture local variations in data. In case of large K, smoother decision boundaries but can miss finer details, which is also called known as underfitting. Now, some of the common practices here are use cross validation to determine the optimal value of K. A common starting point is K equal to root of n, where n is the number of training samples. As per understanding the model's limitation, we have computationally expensive because predictions require distance computations for all training samples. The feature scaling dependence requires proper scaling to avoid feature dominance. And the last limitation is not robust to imbalanced data. Classes with more samples can dominate the predictions. Now that we understand more on K and N, let's go ahead and work on some hands on exercise. First, we will implement KNN for a classification task experimenting with different values of K. So here, the objective is to classify a data set. Example, we can use the iris data set using the KNN algorithm, experimenting with different values of K. So let's write code for that. So I'm going to start with a new file. And first, let's go ahead and import from sklearn dot datasets. I need iris, so I'm going to say load iris. Next thing, we'll need the train test split that is available in sklearn dot model selection. I am going to import train test split. Next, I need the standard scalar, which is available in sklearn dot preprocessing. Import standard scalar. Next, I need the k neighbors classifier, which is available in sklearn dot neighbors. Import k neighbors classifier. Next, I need the accuracy score and classification report, which is in the metrics. So I'm going to say sklearn dot metrics. Import accuracy score and classification report. Perfect. So I have all my, so let's save this in my AI Bootcamp week 5 day 6. I'll call it day 6 underscore ex1.py. So I have my file saved. Now next thing is loading the iris dataset. So I'm going to say load iris dataset. First I'll say data equal to load underscore iris, and then I'll say x comma y equal to, I'll get the data and I'll get the data dot target from this data set. Okay, perfect. So I have both of them. Next, I will split the data set. So let's go ahead and split the data set. I get x underscore train, x underscore test, y underscore train, and y underscore test by calling the train test split method. Give it the same values x, y, test size is 0.2 and random state equal to 42. I think now you can write all these things using your muscle memory. So now next, I'm going to go ahead and scale the features. For that, I'm going to create a scalar variable and initialize the standard scalar. Next, I'm going to say x underscore train equal to scalar dot fit underscore transform and pass the x underscore train to it. Now first do the same thing for x underscore test, scalar dot transform and pass x underscore test to it. Perfect. Now is to experiment with different values of k. So I'm gonna write a comment, experiment with different values of k. For that, first let's go ahead and write the for loop for k in range of, I'm going to use the values 1 to 11, so 1 to 10 pretty much. And here first I will initialize a KNN model. To do that, I can say KNN equal to K neighbors classifier and pass it n underscore neighbors equal to the value of K right now from this for loop. Next, I'm going to say KNN dot fit and pass it x underscore train and y underscore train. Next, let's go ahead and predict on the test data. So we already know that how to do it. We get ypred from knn dot predict x underscore test. Next, I will evaluate performance of each and every. So since it's running in a loop, I get accuracy score from y test and y underscore pred. Can say accuracy equal to this, and next I will print this out. Print f of k equal to whatever the value of k in this particular loop is. I'm going to say for this accuracy equal to accuracy, and I can just say point to f, so 2 decimal places. So that's good. So that should give me my k values, or give me the accuracy based on different k values. So I'm going to go ahead and then make sure I'm in the right folder and say Python day 6 size 1, run it. Takes the load iris data set and it will go through this, and here we have accuracy is 1 for no matter what the value is, because the data set that we have is pretty optimal, and based on that the model kind of gives you this data. So you can try it with the different types of data sets that are available and try to see accuracy, what the accuracy is based on the k values change. So in this case I can just use the value 1 for this particular model. So now our next exercise is to compare KNN results to logistic regression, analyzing the accuracy and other metrics. Now here the objective is to compare the KNN and logistic regression models using the same data set to analyze differences in performance. So what I can do is I can use the same code that we have here and write on top of this. So the only thing that is missing here is from sklearn dot linear model import. I have not displayed the classification report, I only gave the accuracy, but you can also display that based on what we've done in the previous videos. So I need logistic regression so I can compare, and now let's go ahead and train the logistic. So I'm going to just I have my data here, my x-train data here, that's all I need. So I'm going to go here and say train logistic regression model. So for that I'm going to say log underscore reg equal to logistic regression, and here I'm going to say max iterations equal to 200. Now log underscore reg dot fit, I'll fit the data, which is x underscore train and y underscore train. Now I am not using the scale data here, so if I want to use the scale data I can just write this code here, because you have the x train which is scaled here properly. Now once I have that, next step is to predict using logistic regression. So to do that I'm going to say y underscore pred underscore lr equal to, I'll say logistic regression dot predict and pass the value of x underscore test. Next I'll evaluate the logistic regression, so I can say evaluate logistic regression. Now to evaluate it I can say accuracy underscore lr equal to accuracy score, pass the y underscore test and y underscore pred underscore lr. I have instead of equal, so that's why it was giving me error over there. So I have that. Let's print this out. I can say logistic regression accuracy is, it should be 1 itself because the data is pretty prominent for us. This is like optimal data that we're using. Now evaluating KNN using the K from, so we already evaluated using the K values here, but if I want to pick just one, I can always comment this out and then here say evaluate KNN. In this case, we'll use best. I mean, last from our option, everything was good, so I'm going to just use an average of 5 and say KNN equal to K neighbors classifier and neighbors equal to best K. But usually, if you have a different data set and it gave you different values, just pick the best one from there. KNN dot fit pass x underscore train and y underscore train. Next I will say y underscore pred underscore KNN equal to accuracy score pass y underscore test and y underscore pred underscore KNN. Now I can print this. So this is y pred KNN. I think I need to predict first, so I'm going to say KNN dot predict, and to this I'll pass x underscore test to predict. Next I will create the accuracy underscore KNN and pass it this accuracy score that I need, and finally I will print here k dash NNN accuracy for 5, k equal to 5 is in this case I'll say accuracy KNN. It's best to not hard code values, so I can just say this best k equal to accuracy of KNN. Now let's do a detailed comparison of both of them. So to do that I can say print slash, and let's go to a new line, logistic regression classification report. So let's display a report for this. I can say print classification report for y underscore test comma y underscore pred and logistic regression, and same thing for KNN. I'll say KNN classification report KNN, close this. So let me check KNN classification report y test, perfect. So now we can compare and display how both of them fared. So here I'm going to say Python, and there you go. I mean, everything is pretty much one here because we have optimal data available, but you can try it with different data sets and compare logistic regression and KNN in this particular plan. And depending on which works best for you, use that particular model for predicting data sets. So that kind of covers both our hands-on exercises. So just to go over the summary, we went through and understood the working principles of KNN algorithm and its use cases. We implemented the KNN for both classification and regression tasks. Then we experimented with different values of K to observe their impact on performance. And then we compared KNN with other algorithms, in this case logistic regression, and analyzed the results. So we gained insights into the strengths and limitations of KNN for practical applications. So make sure that you use some real data set and play around with and compare KNN and other regression algorithms to kind of understand which one is the best model for you. If you have any problems or issues here while implementing this or have any questions, let me know and I'll get back to you. Day 7, Supervised Learning Mini Project. This mini project brings together the concepts and techniques from the week to build a complete supervised learning pipeline using both regression and classification models. We've gone through a bunch of different things. To close the week, we're going to work on this supervised learning mini project. So the steps that we'll be following is, first is building an end-to-end supervised learning project. Is First step is to define the problem. Identify the objective: regression, which can predict continuous values, or is it classification, where you predict categories? Next step is data preparation. We use the exploratory data analysis EDA that we have learned, where we understand the structure of the data set and then we visualize data distributions and relationships. Next, for pre-processing, we handle the missing values, scale features for algorithms like KNN, and encode categorical variables. Next, for model selection, we go through and choose the appropriate models based on the problem. Example, linear regression for continuous outputs, logistic regression or KNN for classification. Next, step number 4 is model evaluation, where we use performance metrics like mean square error, MSE for regression, or accuracy, precision, recall, and F1 score for classification. Comparison, we compare multiple models to identify the best performing one. Let's talk about applying regression and classification models on a real world dataset. So the dataset options that we have is, for regression example, we'll predict the house prices using features like square footage, number of rooms, and location. And the dataset we are going to use is the California housing market dataset, or any other dataset that you prefer, you can use that. For classification example, we'll classify customer churn based on customer demographic and behavior. And the dataset that we are going to use is the telco customer churn dataset. So let's talk about evaluating and comparing the model performance. The steps that we follow is, first, we evaluate the models using cross-validation. Second, we generate performance metrics, which are MSE for regression, confusion matrix for classification. Next step is summarize findings to identify strengths and weaknesses of each model. Now let's talk about our hands-on project. So our mini project is building a supervised learning model. The objective is to use a data set of your choice to develop, train, and evaluate regression and classification models. For demonstration, we'll use two data sets. For regression, as I mentioned, we're going to use California housing dataset predicting the house prices, and classification, we're going to use the telco customer churn dataset, which is predicting customer churn. Now the task that we're going to work on is, first, we will perform exploratory data analysis and pre-processing. First, we'll do that for the regression dataset, and then we'll do it for the classification dataset together. Next, we are going to train and evaluate multiple models. So first, for the regression, we'll use California dataset, housing dataset, and for classification, we will use telco customer churn dataset. Next, we will summarize the findings in a report. So we'll compare the metrics such as MSE for regression and accuracy, F1 score for classification, and highlight the best performing models and discuss possible reasons for their success. So the task 3 is probably something that I'll leave up to you, and I'll just go over the code right now. So let's go ahead, and I'm going to create a new file, Python file. I'll save it inside my day 7, call it mini project day 7. Now I'll try to write both the codes in one single exercise so we can compare it side by side of how it's done. So first one, I'll say task 1, which was, if you remember, perform EDA, which is exploratory data analysis and pre-processing. So to start with, let's go ahead and import our library. So I'm going to say import pandas as PD. Next, I'm going to import Seaborn as SNS because I need that for plotting. Import matplotlib.pyplot as PLT. Next, I am going to say from sklearn dot datasets, I am going to import fetch California housing. So this will give me the California housing dataset. And again, this is the regression dataset example that we started with. let's say data, this will be load data set, and I'll say data equal to fetch California housing as a data frame. So I'm going to say as frame equal to true. See, perfect. Next, I'm going to say df equal to data dot frame. So I'm going to get my data frame here. Next, let's go ahead and inspect the data. To do that, I'm going to say print df dot info, and also I'm going to say df dot describe. So I have both of them available to inspect the data. Next, go ahead and visualize relationships. For that, I'm going to say SNS dot pair plot. That's what we use for looking at relationships between df, and the variables that I'm going to use here are the columns that are available, and those are, I'll say, medium income. Next, I'm interested in average rooms, average rooms, so average number of rooms that are available. It also has a house age that I can display, and I will say medium house value. Oops, I think I got a typo here. Value, so everything else looks fine, perfect, and then I'll say plt dot show. So that will plot my value. Go ahead and check for missing values. The way you can do that is you can say print missing values is /n comma df dot is null. This is a function that is available, and I want to sum of all of them, how many are missing. So that's what I can check. I can go open my terminal, make sure I'm in the right folder, Python mini project, run it. It's going to give me my info, my my description. Next, it's gonna plot me my graph, which you probably saw, of all the data that is there. I can probably try to make it smaller, but it's difficult. Okay, there you go. So medium income, average room, so whatever I mentioned over there, it created a plot of that. And then finally, when I close it, I'm going to check what is missing, and nothing is missing, everything is available. The missing values is 0. So next, for our classification data set, I mentioned that we're going to use the telco customer churn.csv. But that file I have downloaded from the internet, and that is available in our folder here inside day 7. So I have this data set which talks about customer ID, the gender, age, tenure, monthly charges, total charges, contact type, payment method, and churn is 1 and 0 depending on if they're going to churn or not. So what I'm going to do is I'm going to load that data set here. So I'm going to go here and I am going to say load telco customer churn data set. Now if you have another data set, just use that, but I'm going to use this, and to do that I can say read CSV file, and I can pass the name of that file, which in this case is, let me open that again. So I'm going to paste that here. So this is the file that I'll open, and this will have our data. Let's just, for the sake of it, let's go ahead and make sure, first of all, I'm not using the same name. I'm going to call it telco, and here I am going to say inspect the data. To inspect the data, I am going to say print df underscore telco dot info, something similar to what we did before, df telco dot describe. So same as what we did with the previous data set, I'm going to do the same thing. Now next thing, I want to visualize churn distribution. So I am going to say SNS dot count plot. That's what I'm going to use. And here I'm going to say x equal to, now the field name, can open this and I can see churn, and that's what I want to use. So I'm going to say churn churn data equal to df underscore telco plot dot title is churn distribution. That's what I'm displaying. Now I'm going to say plot dot show, and let's see, handle the missing values. Again, I'm going to say df underscore telco dot fill na. If there's some values that are not available, looks like I have pretty much all of them, but I have a lot of data here, so it's very difficult to check it. So if there's something missing, I'm going to say df underscore telco dot use the mean value, and in place change it in place equal to true. So there you go. So that will change the value of that if there's any missing values over there. I can also run this. I can make sure the previous one is not being displayed, and go here, clear it out, and run that file again. And there you go. We have the churn distribution of not buying and buying over here displayed in a plot. And here is all our data set, which talks about, oh, these are all non-numeric, so that's why I'll have to change that to scale, but I'm going to ignore that for now and clear it out. Go next. So the next step is to train and evaluate multiple models. What I'm going to do is I'm going to divide this project into two, just so that it's not confusing. So I'm going to call it mini underscore project underscore day 7 underscore telco. Let's call it telco dot py, and take everything from here, move it here, and here make sure that I'm going to get rid of the telco stuff, and this one I will uncomment it because this is my data for my current project. So I am going to remove cbon, things that we don't need, we can get rid of that. Pandas, we don't need it here, it's all needed in this project, so that's why it's there. I am going to get rid of, for my telco project, I'm going to get rid of my iris, did we the California data, so I'm going to get rid of that, not needed. cbon, we are using it, so perfect. So this is how we'll keep it separate. So let's go ahead and train and evaluate multiple models for our first California housing data. So for that I need some stuff like I need the train test, so I'll get it from sklearn.model selection, import, and train test split. Next, from sklearn dot linear model import, I will import the linear regression because that's one of the things that I'll test. And from sklearn dot metrics, I am going to import mean squared error. So that's what I'll take. And now let's define our features and target. So to define our features, I am going to go after our data set is available here. I am going to say x equal to df of, now I need medium income, which is here, medium income. I need house age, which is here. So these I'm going to set them as my features, and average number of rooms I'm going to also take that, doesn't matter the order here. Next I'm going to say y equal to df of and here I'm going to use the medium house value, which is this, as my target value. So here let me add define features and target. So I have that. Once I have that, I need to split the data. I can also do that here. I don't care about all these things here, but I can pretty much comment this out. And then I'm going to say split the data set. The way to split is, fix this, is x underscore train, x underscore test, y underscore train, y underscore test. And this is coming from is train test split function. Will pass x, y will pass the test size equal to 0.2, then we'll say random state equal to 42. So that's perfect. Next, go ahead and do train the linear regression model. Now to do that, I'll say model equal to, first initialize it, linear regression. Next, I'm going to say model dot fit, and to this I'll pass x underscore train and y underscore train. So I gave the features and the target for it to train. Now let's make predictions. Make predictions y underscore pred equal to model dot predict, and to this I'll pass x underscore test. Perfect. Now let's go ahead and evaluate performance. So do that, I'll say MSE equal to mean square error, and to that I'll pass y underscore test and y underscore pred to validate, and let's print the linear regression MSE is MSE. So there you go. So we printed that out. Now if I want to do the same thing for the telco customer churn data, I'm going to go here. Let's try to take as much as possible from here. I am going to use, okay, looks like this is not plotting. Oh, we have commented that code, so I'll keep that there. I need train test split, so I'll use that. I need, okay, let's say from sklearn dot pre-processing, I would need to import standard scalar and label encoder for the field that are not not numeric. So next I need sklearn dot linear model import logistic regression. Next I want to get from sklearn dot neighbors, I am going to import the k-neighbors classifier, so that's what I need. And finally, let's get the metrics. sklearn dot metrics, I will get import classification report, and I'll also use confusion matrix to display the data accordingly. Now, first thing, we need to encode the categorical variables. So for that, I will take the, so data is here, I'm printed the data here. So let's go ahead and say encode categorical variables. Now to do that, I can say le equal to label encoder. I'll initialize that, and then I'll say df churn, make sure le dot fit transform, and to that I'll pass df churn. Oops, it was churn. Of course, I forgot that it was not df, it was df telco, and equal to here. So this will make sure it's all categorized. Next, I want to define the features and the targets. So I am going to say define features and target here. So x equal to, from my data set, I am going to say drop columns equal to, I will drop the churn column from the data set df telco. Next, I will say y equal to df underscore telco. I want only churn here. So perfect. So that will, now let's go and scale the features. So I'll say scale features. I'm going to say scalar equal to standard scalar. Next, I'm going to say x equal to scalar dot fit. So transform the data that we have, that is in x. Perfect. So that's done. Next, let's go ahead and split the data set. To do that, again, I will just copy paste from here, since it's a long line. You can just copy this, paste it here, x train, y train, and here we have x, y, test size. Everything is same based on the parameter that we have defined. So perfect. So next thing that we need to do is train the logistic regression model. So I'm going to say train logistic regression model. Now to do that, I'm going to say log model, logistic regression model equal to logistic regression and pass it max underscore iterations equal to 200. Next, I'm going to say log.model, log underscore model dot fit. I need to fit x underscore train and y underscore train. So my model is trained with the right data. Now let's train with the KNN model, since we need to compare both of them. So I'll say KNN model, KNN underscore model equal to K neighbors classifier, N underscore neighbors equal to, let's set it to 5. And KNN underscore model dot fit, and now train with the same x underscore train and y underscore train. Now let's go ahead and evaluate models. Now we have two different ones. We have logistic and we have KNN. So first let's start with log underscore pred equal to log underscore model dot predict with x underscore test data. Same thing, but for KNN pred equal to, instead of log, I'll say KNN model dot predict x test. So this will do that. Next, I'm going to go ahead and print /n logistic regression classification report. This report I will print right here by saying classification report y underscore test and pass it log underscore pred. Now similarly, next one is for KNN. So I'm going to say KNN not regression classification report y test and KNN underscore pred. Pass that. Let's also display the confusion matrix for logistic regression. I'll say print confusion matrix is /n comma confusion matrix, and it needs y underscore test comma log underscore pred. Perfect. I am going to comment out the rest of the code here because that's from the first step. So our task 2 is over, but let's run it just for the fun of it. Say Python mini project telco, and there you go. We have our KNN classification report for the code, and we also have the logistic regression and confusion matrix is right here based on true negative, true positives, false negatives, and false positive values here. Perfect. And since we are using real data this time, a CSV file, not everything is 1.0, but it looks pretty close and looks good that we have something that looks more realistic. Our next step, or task 3, is to summarize findings in a report. Now this is something that you probably have to do it yourself, where you compare the metrics such as whatever we did here, MSE for regression and accuracy, F1 score for classification, and highlight the best performing models and discuss possible reasons for their success, and share that with your business units, and they will decide which model they want to use, or you can give them your decision of which model you'll be using. So that's the entire flow for this mini project where you're building a supervised learning model. So just to recap, today we in this mini project, we applied end-to-end supervised learning techniques to real-world data sets. We performed exploratory data analysis and pre-processed data set effectively. Then we trained and evaluated both regression and classification models. Finally, we compared models using performance metrics and summarized findings in a comprehensive report. This kind of helped us develop our ability to handle the entire machine learning pipeline from data preparation to interpretation. So this is what a data engineer or data scientist does when they build a particular model, or they kind of suggest a particular model to the business units. Let me know if you have any questions or problems or issues, and I'll get back to you.